Hello everyone, this is 8th week and we are in 4th lecture of 8th week, and overall it is 39th lecture of the course Process Equipment Design, and I welcome you all in this lecture. So as far as this lecture is concerned, in this lecture we are going to cover the topic crystallization. Okay, so in this lecture we will define crystallization, we will see different form of the crystal, and then we will discuss the crystallization process depending upon the solubility curve, right? And after that in subsequent lecture we will discuss about the design of crystallizer. So let's start this lecture with crystallization. So what is basically crystallization? Crystallization is the process to form the product in a definite shape. Okay. Usually we do not focus on the shape, whatever product we want. If that product is of given quality or the acceptable quality, we consider that. But in chemical engineering process, some of the products are formed in a definite shape. I am not speaking about the size may vary, but shape will be very definite. Okay. So that shape we call as a crystal. Okay. When the product is made in the form of crystal, the process by which it is made, we call that as crystallization. So in this lecture we will consider the crystallization process in detail. So let's start that. So as I have told you that finished solid products of chemical process industries often come in the form of the crystal. Okay. So basically if I am saying a crystal, it means it has a definite shape. What these shapes are, that we will discuss. So as far as a crystal is concerned, it is a solid body with the lane faces in which the atoms are arranged in an orderly repetitive array such as cubic, tetragonal, hexagonal, etc. So you see it has a definite array. Okay, whatever particles are available in the product, that takes these particles take its step in a definite array, or we can say in a definite format, and so we call that as a crystal. Okay, and that array may be a cubical shape, a hexagonal, octagonal, or you can say any that kind of shape, but or you can say any other shape, but that shape is very definite. Okay. So what is basically crystallization? The crystallization is the process of formation or production of crystals from a solution. We consider that as a crystallization. Okay. So that is basically when feed is available, it is in the form of solution, but the product is in the form of solid. Okay. So that we consider as crystallization process. And if you see in this image, we have several general crystal system such as cubic, tetragonal, orthorhombic, monoclinic, and similarly we have many others. Okay. So these shapes are very definite. Okay. So if I give some example, if you say that you are dealing with mica, for example. Okay. So what is the shape of mica? Okay. The shape of mica is a plain sheet. Okay. When you break the mica particle, it will be in the form of fine sheets. Okay. So in that way we consider that it has a definite shape. In the similar line we can come across with different other examples also, right? So that is basically a particular crystal. Fine. So as far as crystallization process is concerned, it is used to obtain material in attractive and uniform crystals of good purity, separating a solute from the melt or solution and leaving impurities behind the process by which a substance in solidifying assumes the form and structure of a crystal or becomes crystallized. So you see, when we have the solution and the product mainly consists of the solute which is available in the solution, right. So, when that solute takes a definite shape of a particle, it leaves the solvent behind, okay, and we consider that particle and we consider that solute is crystallized, right. So, we have different examples of the product which are available in the form of crystal, and these are when we consider the sodium chloride, sodium, aluminum sulfates and sugars. Okay. So, when you consider the manufacturing of the sodium chloride, or we can say the sugar, it has a definite shape, right. So, in these industries, crystallizer a very important unit, and which is usually occur after the evaporation, because when we have the evaporation, we got the solvent. When we have the evaporation, we got the solution with high concentration, right, and that concentration is sufficient to be used in crystallizer. So, usually in sugar industry, we can say sodium chloride industry, there we consider crystallizer as a main unit. Okay. And secondly, we can consider crystallization as a purification of many organic liquids. Okay. So, when we purify the organic liquid, how we remove the impurity, that is done through crystallization. Okay. Because when we have the solution, impurity can occupy a particular shape, and that can be removed in the form of crystal. So, when solvent is available, we consider that as a pure organic solvent, and that can be purified by the crystallization process, right. Further, we have different applications of crystallization, such as it is used to freeze concentration of a fruit. It is used to freeze concentration of the fruit juice, desalination of sea water, as I have told you that it is used to prepare sodium chloride, and further we can also consider this to remove the impurity and to generate the drinkable water from the sea water. Okay. So, it is also the part of the crystallization, but mainly it is not used to prepare drinkable water, it is basically used to prepare the solid which we consider as sodium chloride, right. It is further used for recovery of valuable materials such as metal salts from the electroplating process. So, you can consider that crystallization is used in different processes in chemical industries. So, now we will see that how this crystallization occurs. So, for that we will consider on the solution where I am having a particular solute, right. So, when the concentration of the liquid solution is increased, okay, and how we can increase the concentration of the solution, either by evaporation of the solvent or by cooling or the combination of these two, right. So, the solution gradually reaches the saturation level. When we further evaporate it or cool it, it attains a degree of supersaturation. So, that is very important word when we are considering crystallization, the solution should be at supersaturation condition. Okay. You may consider that the solution of sugar in water, right, at a particular temperature, when you keep on stirring, the sugar is mixed in the solution. Sugar is mixed in the water very easily and form a solution. Okay. When you keep on increasing the temperature, the solubility of sugar in the water will also keep on increasing, right. So, more and more sugar can be put in the water and solution can be obtained. Okay. Now, when we further decrease the temperature of the solution, then what will happen? Whatever sugar is available, it will be available in the form of precipitate, because further it will not be soluble anymore, because temperature we already have reduced, right. So, in that case you can see small particles of sugar in the solution, and that particles are basically the crystals. Okay. So, how it happens? Because we reduce the temperature, and when we reduce the temperature, the saturation condition becomes super saturation condition. Okay. So, that is very common example of crystallization process that you can carry out at your houses also. Okay. So, let us discuss it further. If the concentration of a solution is more than the solubility of the solid at a particular temperature, it is called as supersaturated solution. So, as I have told you, as I have explained this to you with the example of sugar and water. So, you can consider the supersaturated condition in that solution. Okay. So, further if I consider the example of sugar solution, it can have a high level of supersaturation. The concentration may even about 80% more than the saturation value. But in the solution of sodium chloride, the maximum attainable supersaturation is too small to be measured. Okay. So, in sugar solution, supersaturation condition occurs with significant amount of sugar. However, that is very less when we are considering sodium chloride. Okay. So, basically what happens in crystallization is spontaneous formation and growth of tiny crystal, spontaneous formation and growth of tiny crystals, which we call as nuclei, take place in a supersaturation solution. Okay. So, when we consider the supersaturation condition, it means that whatever solid, it means that whatever solute is available, it forms crystal. Okay. But crystal has a definite size, right. Initially it is not in the form of crystal, it is very small particles. Okay. Or we consider that as tiny crystal. In other word, it is called nuclei. So, initially very small particles are formed, and then continuously formation of solid, and then continuously formation of solute over the surface of tiny crystal. We have definite size crystals, but it is basically start on the nuclei, right, and that occurs at supersaturation condition. So, the suspension or slurry containing the crystals, the solution is called magma. Okay. So, when we have the solution and when we have the supersaturation solution, and when I am having small crystals in this, we consider that as a magma, right. And when the crystal is removed from the solution, whatever liquid remains there, okay, that we consider as solvent, or that is also called as mother liquor. Okay. It does not mean that solute will not be there, solute will be there, but solute concentration in the mother liquor is very less, right, because most of the solute we can remove in the form of crystals. So, you see, usually it has three component. First is crystal, second magma when we have the solution along with crystal, and third we have the mother liquor when crystal is removed from the solution, right. So, as far as crystallization process is concerned, it has different steps. So, process of production of crystal, the first step is the crystallization itself. Then we have separation of crystals from the mother liquor. Then washing of the crystal with fresh solvent to remove the impurities from the crystal, and then dry the moist crystals. So, in this way we have different steps which we should follow to make the product of different shapes that we consider as crystals. Now, let us see few points about supersaturation. Okay. So, what is supersaturation? A solution that is in thermodynamic equilibrium with the solid phase of its solute at a given temperature is called as saturated solution. Okay. When the solution, when the solvent and solute is at equilibrium condition at a particular temperature, that is very important. At a particular temperature, we consider that as a saturated solution. Okay. And when the solution considers more solute, okay, when the solution considers more solute than that is available at equilibrium condition, we call that as supersaturation condition. So, what is the degree of supersaturation? That must be the concentration at present when I am considering it a supersaturation solution and the concentration at the equilibrium condition when it is a saturated solution, right. So, degree of saturation. So, degree of supersaturation is basically C minus C star, where C and C star are the solution concentration which is at the supersaturation condition and the equilibrium saturated value, that is this value, right. So, difference of these two will be the degree of supersaturation, and further we have supersaturation ratio which can be represented as S, and a relative supersaturation psi we can obtain as, here I am having capital S which is the supersaturation ratio C minus C star, and then we can have relative supersaturation, that is psi value. So, that is basically delta C by C star. So, you can consider that C minus C star divided by C star. So, that this is nothing but the S minus 1. So, simple derivation is there. So, in that way you can relate relative supersaturation and supersaturation ratio, right. And now we have very important diagram, and this diagram we consider as solid liquid phase equilibrium. Okay. So, if you focus on this particular graph, it is showing naphthalene benzene binary system. Okay. And binary system for what? This is basically solid liquid phase equilibria. Okay. So, when we consider temperatures as well as concentration of the solution, solution means when I am having naphthalene in benzene. So, naphthalene is solid, benzene is solvent, right. So, when I am considering this graph, if you focus on this line, that is A to E and then B. Okay. This particular graph from A to E and then B, this graph we consider as solid liquid phase equilibria line, right. And above this we consider unsaturation condition, and below this we consider supersaturation condition, right. So, this curve basically we call as saturation condition also. Okay. So, let us see if I am having point P1 in this, fine. So, this point P1 is at high temperature, and when we cool this, okay, when we cool this it will reach to P2 point. Okay. So, while reducing this we can consider that the solution from unsaturation condition can be reached at saturation condition at point P2, right. So, this is the case when naphthalene is dissolved in benzene. So, here I am having a saturation solution. Now, if we further cool it, okay, if we further cool it, then what will happen? In the same concentration we are reducing the temperature, it means this is the condition where crystal will be formed, and this particular region we call as supersaturation condition. So, at this point when we reduce the temperature further, the crystal of naphthalene will form. Okay. And as far as saturation condition is concerned, we can have saturation condition while varying the concentration at different temperature from B to E. Okay. And this is basically concentration of the solution. And in the similar line, when I am considering point P3, let us say. Okay. So, in this point P3, when I am reducing the temperature further, it will reach to point P4. So, P4 is basically the saturation point where it is available at saturation curve. Okay. When we further reduce its temperature, then what will happen? Here benzene will be solidified or crystal will be formed of the benzene. Okay. So, here you see we can have the crystal of the naphthalene, but here we have crystal of the benzene, and all these will depend on the temperature and concentration. So, this point this curve from A to E, it is basically the saturation condition where temperature and concentration will vary. Okay. Now, when I am considering point E is basically called as eutectic point. Okay. And when we consider this point E and reduce the temperature further, we consider this section when the whole solution is solidified, either it is benzene or naphthalene. Okay. So, beyond point E, whole solution will be solidified. However, above point E, it will depend on the curve where naphthalene will be crystallized or where benzene will be crystallized, right. So, in this way we consider solid liquid phase equilibria, and this curve directs us that at what condition we can form the crystal of a particular solute. Okay. So, and further we will discuss the solubility curve. Okay. So, basically what is solubility? When we consider the solubility, it is basically the ability of a solute to dissolve in a solvent, okay, and that we consider as solubility. Now, here we will discuss the solubility curve. If you see this, here I am having temperature as well as concentration. So, the solubility of the material is the concentration of solute in steady state saturated solution at any given temperature. The solubility of solid generally increases with increasing temperature. So, I think this is the known factor. And further, if we focus on the solubility curve, here I am having three different conditions. First is the stable condition where crystal cannot nucleate or growth. Okay. So, that is basically the solution is at saturation condition, or so solution is at saturation condition or less than that, right. So, next is we are having metastable state where crystal can grow but cannot nucleate. It means crystals are formed randomly. Nucleation means first tiny crystals will be formed, and because over that solute will be deposited. So, in metastable state we do not have any nucleation, crystal are formed randomly. Okay. And next I am having unstable condition where crystals can nucleate and grow spontaneously. Okay. So, this is basically the solubility curve where you can focus that at a particular temperature how much solute should be involved or should be dissolved in the solvent so that crystals can be formed. Okay. So, this is the basic aim of the solubility curve. Okay. Next we have some important factors which affect the apparent solubility, and these are the supersaturation, the very important point. Simple dissolving a solute in solvent, especially if you use agitation, heat or ultrasound, will usually create a thermodynamically unstable, that is supersaturated solution. Okay. So, next point we have the purity. So, generally speaking, the purer the solute material is, then the lower its solubility will be. Okay. And it will also depend on the measurement method. The apparent solubility can sometimes vary depending on how you measure it. So, along with this there are number of factors on which the apparent solubility depends, and these are polymorphic form. So, most solutes will have many different polymorphic form, and that we consider as the crystal with widely differing solubilities. Okay. And now we have the particle size. Very small particles can be much more soluble than the larger particles. So, it will depend on the solute particles, and so solubility will depend on the solute particles also. Okay. And then we have the chemical stability. Reactions can occur between solute, solvent or environment. So, we should not consider that. So, basically we should avoid the chemical disability. okay, and we should consider that solute solvent should not and we should consider that solute solvent should not react with the environment or react with each other. Okay. So, all these factors depends on the apparent solubility, and now we will discuss nucleation and crystal growth. So, as far as nucleation is concerned, basically we have two types of nucleation. The first is the primary nucleation, and then we have the secondary nucleation. Okay. What is primary nucleation? Primary nucleation are that nucleation where the nuclei is not available. Okay. It means the crystals are formed randomly, and secondary nucleation means some nucleates or nuclei are already available and further growth of the crystal occurs on these nuclei or nucleates, right. So, secondary nucleation means when I am already having nuclei inside this, and primary means nuclei are not available, crystals are formed randomly. Okay. So, as far as primary nucleation is concerned, it is basically of two type, homogeneous and heterogeneous, and secondary nucleation can form in the form, and secondary nucleation can occur with the contact, with shear, fracture and attrition. Okay. So, these are basically nucleation mechanisms which are considered in crystallization process when the solution is at supersaturated condition. Okay. So, what is primary nuclide? Basic difference I have. So, what is primary nucleation? Basic definition I have already told you. Now, see its further. So, classical theories of primary nucleation are based on sequences of bimolecular collision, interaction of supersaturated fluid that result in the buildup of lattice structured body which may or may not achieve thermodynamic stability. So, such prime nucleation is known as homogeneous nucleation. Okay. So, as far as homogeneous nucleation is concerned, so in this nucleation a consideration of the energy involved in solid phase formation and in creation of the surface of an arbitrary physical crystal of the radius r in supersaturated solution gives. So, as far as energy involvement is considered, it is basically pi by 4 r square sigma plus 4 pi by 3 r cube delta G V. Okay. So, what these parameters are? Let us see that G is the overall excess free energy associated with the formation of crystalline body, right, and sigma is interfacial tension between crystal and the solution, and further G V is the free energy change per unit volume associated with the phase change. So, in this way you can compute the energy involvement when I am considering homogeneous nucleation. In the similar line, heterogeneous nucleation is the presence of foreign particles or heteronuclei enhances the nucleation rate of a given solution. The equations similar to those for homogeneous nucleation have been proposed to express this enhancement. Further, results is simply a Further, we can consider the result is simply a displacement of nucleation rate against the supersaturation curve. Okay. So, you see here I am having this expression where Kn is the primary nucleation rate constant and delta C is the order of nucleation process. Okay. So, in this way you can consider homogeneous nucleation and heterogeneous nucleation. So, let us focus on secondary nucleation. As I have told you, it is developed based on some nuclei or nucleates, right. So, secondary nucleation can by definition take place only if crystal of a species under consideration are already present. So, that I have already told you, and since this is usually the case in industrial crystallizers, secondary nucleation has a profound influence on virtually all industrial crystallization processes. So, at industrial level we usually consider secondary nucleation, okay, because in that nuclei are already available. Okay. So, we will discuss the concept of crystallization and design of crystallizer in subsequent lectures also. So, that is all for now. Thank you.